Welcome, everybody. It's my pleasure to introduce Melanie Weber, who will be speaking today about exploiting geometric structure in matrix-valued optimization.
Thank you. Thanks for having me and for the invitation to speak. So as was just said, and as the title of my slide here indicates, we're going to talk about matrix-valued optimization, and particularly taking a geometric perspective on this problem. And all the work that I'll be talking about today is joint work with Suvrit Sra, who's a professor at MIT. So let me first start with some motivation. So where do we encounter optimization on over matrices, or in this case, we will be particularly viewing these problems as optimization on matrix manifolds. So in particular, in machine learning applications, we encounter matrix-valued problems either as standalone algorithms. So many machine learning algorithms can be formulated as a matrix-valued optimization routine, or sometimes machine learning algorithms have a subroutine that can be phrased as a matrix-valued problem. Some examples you see here on the slide, many of which I'm sure you have encountered at some point, like perhaps minimum bisection of graphs or k-means clustering. So those are very classical problems, and all of those can be viewed as an optimization on matrices. So now when we want to solve such optimization problems, we could take a Euclidean perspective. So we could say that matrices are vector spaces, so we can use Euclidean optimization algorithms to solve them. In that case, the class of matrices over which we're optimizing enters as a constraint. So for instance, if we want to solve an optimization task over orthogonal matrices, then we would impose an orthogonality constraint. And then it has been realized that we could also rephrase those problems on a suitable manifold. So the orthogonality constraint, or the class of orthogonal matrices, corresponds to a manifold, right? The manifold of orthogonal matrices. So we could rephrase our problem over that manifold of orthogonal matrices, let's say. So in that case, we would be solving an unconstrained optimization problem, since the class constraint of the matrices is already encoded in the parameterization of our problem, right? So in that case, instead of solving a Euclidean constraint problem, we would be solving a Riemannian unconstrained problem. And in general, if you've done optimization before, it's usually easier to solve an unconstrained problem as opposed to a constrained problem. And that observation has been driving a lot of the early research on Riemannian optimization. And then there are also sometimes other algorithmic benefits that we can get from this reparameterization that have to do with the convexity of the problem. And a lot of the examples that we see throughout the talk exploit exactly those better convexity properties that we have in the Riemannian setting. So in particular, the talk today will have two parts. In the first part, we will talk about constrained Riemannian optimization. That is motivated by the observation that in a lot of these practical problems where we encounter matrix-valued optimization, we actually have additional constraints. So in addition to the constraint that sort of defines what class of matrices we're working with, there are other constraints, perhaps on the determinant of the matrix or the norm of the matrix. And these additional constraints have to also be handled. So in a sense, what we're solving in the Riemannian setting is not exactly an unconstrained problem. There are additional constraints that we have to take care of. And in order to handle this, we have to develop constrained optimization methods. Now you might ask, we've done this reformulation to get rid of the constraints. That's true. But in these constrained Riemannian optimization methods, as we will see, we can still exploit these better convexity properties, geodesic convexity, which in some of the examples that you see here on the slide is the case, and we will see that also in numerical examples. And then in the second part of the talk, we will exploit a different structure that we find in a lot of matrix-valued optimization problems. Namely, very often our objective functions can be written as a difference of convex functions. And then we can design algorithms that particularly exploit that structure. And here again, we will make use of better convexity properties that we have in the manifold setting, and we'll show that that allows us to give precise convergence guarantees for such algorithms. So before we get started with part one, I want to say a few more words on those convexity properties. So I'm sure everybody in the audience is familiar with the concept of convexity, so knows what a convex function is in the Euclidean setting. Now, if we are on a manifold, we have an essentially analogous definition of convexity. So you might recognize this condition that we have here. It looks very similar to what we have in the Euclidean setting, but now we are checking this convexity condition not along a straight line, but along a geodesic. So basically, we look at 2 points on a manifold, right? And the shortest path between those 2 points along the manifold can be characterized by a geodesic between them. And then we check our convexity condition for a function defined on the manifold along that geodesic. And that notion of convexity has in the optimization context the same nice properties that we also have in the Euclidean setting. So if our objective function is convex, we are guaranteed to have a global optimum. And that means that if we have a first order method that finds a local optimum, we are guaranteed that that local optimum that we found is also the global optimum, meaning that our first order methods from essentially any initialization will converge to the global optimum. And that's, of course, highly desirable, right? Because in that case, we don't have to be careful with how we initialize our algorithm. We can just find one feasible initialization and we're guaranteed to converge to the global optimum. So it's always preferable in the optimization context to work in the convex setting. So if there's any reparameterization of our problem that we can find such that we're in the convex setting, then we should always do that. Okay, so as I said in the first part of the talk, we will look at constraint optimization on manifolds. So the class of problems that we're considering is written here. So we have some function defined on a manifold. Usually we constrain ourselves to Riemannian manifolds. So let's say for now M is a Riemannian manifold, and we assume our function to be smooth, but it doesn't have to be necessarily convex. Of course, in the convex setting, we have good properties, but a lot of the algorithms that we will see can also work in the non-convex setting, just with less good convergence guarantees. And then we're in the constraint setting. So what we say is that the minimum that we want to find has to lie in some region on the manifold that we denote as script X. And that region on the manifold has to be compact and convex. And problems of that form occur in many settings. So we've seen some examples of matrix valued problems and already, but it's really that class of problems is much broader. So for instance, there's been recently a lot of interest in studying sampling algorithms through a Riemannian lens. So many sampling algorithms can be seen as an optimization in Wasserstein space, so in the space of probability densities. And then tools from Riemannian optimization can be used to understand the convergence rates of such optimization routines and can then be used to derive convergence guarantees for sampling algorithms. And then more generally in the machine learning context beyond matrix manifolds, there are also hyperbolic spaces, for instance, so spaces with constant negative curvature that have seen a lot of interest in machine learning, and training a machine learning model on such manifolds, for instance, can also be phrased as a Riemannian optimization problem. So there are many use cases for these algorithms. So if we want to design a constrained optimization routine for manifolds, the first sort of natural step is to look at what has been done in the Euclidean setting. And in the Euclidean setting, of course, constrained optimization is a very well-studied problem. So some of the early algorithms that are still widely used today go back 50 or 60 years. So in the Euclidean setting, the general algorithms that we find roughly split into two classes. projected gradient methods and projection-free methods. Projected gradient methods are essentially extensions of the gradient descent algorithm to the constraint optimization setting. So the general idea here is as follows. So imagine we are in iteration k, and we are at a point at an iterate xk, and then we evaluate the gradient at that point, and that gives us a feasible descent direction to step into. And then we perform a standard gradient descent step, right? So we step with a certain step size in the direction of that gradient. And then, of course, that hasn't taken into account any of the constraints. So imagine we are in a setting like in this little sketch here, where our constraints are valid in this blue region here denoted with script x. And then that gradient descent step has not taken into account whether or not we are in the feasible region. So it might happen that we step out of it, and in that case, we have to project back onto that feasible region. So we have to compute some kind of projection. And then, of course, depending on the geometry of our constraint set, the geometry of our feasible region, that might be efficient, it might be possible to efficiently compute that, might be simple, or it might be very expensive. Now, if we're in the Riemannian setting, if we're on manifolds, there's been a lot of work on extending gradient descent to manifolds. So that's a very well-studied Riemannian algorithm. But it turns out that if we're in the constraint setting, computing that projection in the manifold case is quite hard, quite expensive to do. So that is an approach that's often not very efficient in the Riemannian setting. Now, an alternative to projected gradient methods are projection-free methods. So here the prime example is the Frank-Wolfe method. Again, let's look at sort of the high-level idea. So again, after k iterations, we are at an iterate xk. We can again compute the gradient and evaluate that to find a feasible descent direction. But now we take the constraints into account at the very beginning by searching along the feasible descent direction and finding a point that just fulfills the constraints. So in our sketch here, we want to find the point that lies on the boundary of our feasible region in the descent direction. So that would be the point that just fulfills the constraint. And finding that point is implemented by a subroutine called the linear oracle, which is written here. So basically, our first step in the Frank-Wolfe algorithm would be to call the subroutine and find this point set k. And then in the Euclidean setting, we just linearly interpolate between our point xk and that point set k that the linear oracle returns. And then we step along that line with a certain step size, usually chosen to be something like 1 over k. And that gives us a point in the feasible descent direction, but that is sufficiently far away from the boundary, which is something we want to avoid for technical reasons. So we don't want to get too close to the boundary. So by setting some step size like 1 over k and then having that decrease as we do more and more iterations, that keeps us sufficiently away from the boundary. So notice here, since we have assumed that our constraints are convex, right? So any point along that line that we're constructing here will be in the feasible region. So there can never be a step where we go outside of the feasible region, and therefore we don't have to compute any projections back onto the feasible region. And as a result, that's why those methods are called projection-free methods. We never have to compute a projection. So in practice, when we evaluate which kind of algorithm to use, what we basically have to compare is the cost of computing a projection versus the cost of solving that linear oracle. And in the Riemannian setting, solving that linear oracle can usually be done fairly efficiently. We'll talk about that in a few slides. There are even some cases where it can be done very efficiently, but more on that later. So to extend this algorithm to the Riemannian setting, we have to look at the two key steps in the algorithm and sort of generalize them to manifolds. Sort of the first key step in the algorithm, as we said, is this linear oracle. So we can generalize that to the Riemannian setting by evaluating the Riemannian gradient instead of the Euclidean gradient, and then searching along a geodesic instead of a straight line in the descent direction. And then also the linear interpolation between our iterate xk and the point zk that the linear oracle returned has to be replaced by a geodesic interpolation, which is written here. So here the exponential map characterizes, in a sense, the shape of the geodesic. So that is manifold specific. It's written here in the general case. And then if you're on a specific manifold, like the manifold of positive definite matrices, for instance, then that exponential map would have a specific form. So that algorithm is a useful extension of the Euclidean Frank-Wolfe algorithm in the sense that it recovers the same convexity guarantees. So in particular, a first order method like the Frank-Wolfe algorithm should have sublinear iteration complexity, which we can show is the case for the Riemannian Frank-Wolfe algorithm. So sublinear rate here means that after k iterations, the value of our objective function is about on the order of 1 over k close to the optimal value. Right, so that means that the error, in a sense, of our objective value decreases at a sublinear rate. That's why we call it sublinear iteration complexity. There are also settings where we actually have a better iteration complexity, namely if we're in the following setting. So if we have actually stronger convexity properties of our objective function, called strong convexity. So here, the first part that I've written here is equivalent to the geodesic convexity notion that we saw a couple of slides ago. And then we have here an additional term that makes that condition more stricter, depending on how that parameter mu is set. So there are objective functions where in the Riemannian setting or the equivalent notion in the Euclidean setting, we can find a mu such that that convexity condition holds. And if we're in that setting and we know that the optimum of our function does not lie on the boundary of the feasible region, then we can show that the algorithm even converges at a faster linear rate. So in some settings, and that's a setting that sort of occurs quite frequently. So for instance, the barycenter problem that we will look at in a couple of slides is one such case where we have mu strong convexity, and in those settings, the algorithm is very fast. Now, the complexity of the algorithm that we have looked at so far was measured with respect to the number of iterations that we need to find the optimum. Another thing that we have to pay attention to is the computational cost of actually computing one of those iterations. And in this algorithm here, that is very strongly dependent on the cost of the linear oracle, right? So that goes back to what we said earlier about projection-free versus projected gradient methods, where in that case, the cost of each iteration depends very much on the cost of computing that projection or on the cost of solving the linear oracle. In the Euclidean Frank-Wolfe algorithm, that is a very popular algorithm for constrained optimization in the Euclidean setting because that subroutine can be solved very efficiently. It's a convex subroutine, so with standard solver that is usually very, very quick to solve. In the Riemannian setting, the problem is non-convex, so it's a little bit harder to solve, and we have to think more carefully about how to implement this. So here is again written that is the subroutine that we wanna solve, right? Just as a reminder. And there are two approaches that we could think about. So we could call kind of an optimization routine within an optimization routine and try to find an approximate solution to that subroutine, right, with an off-the-shelf solver. So in that case, that would give us some approximate solution to the linear oracle, and then if we plug that approximate solution into our overall optimization subroutine, we have to think about how that approximation error might impact our overall convergence rate. Or what sort of the ideal case is if we could actually find an exact solution to that subroutine, ideally in the sense of a closed form solution, and then there wouldn't be any approximation error, of course, and then also a closed form solution, of course, is much faster to implement. So from a computational perspective, that would certainly be preferable. So if we're in the setting where we don't have a closed form solution, we can only approximately solve that subroutine. As I said, we have to think about how the approximation error might impact our overall convergence rate. We have analyzed this and shown that actually it doesn't hurt us too much. So we have here like some notion of measuring the approximation error. So we have like an additional term here on the right-hand side that kind of measures how far from the exact solution of the linear oracle we are at. And as long as that delta is not too large, we see that we can still recover the sublinear iteration complexity. So we still converge at a linear rate, just with slightly worse constants. And in practice, we see that that is also what we see numerically. So if we use some off-the-shelf solver, depending on which specific manifold we are working on, we still see like good convergence rates. So that is certainly a practical approach for how to use the algorithm in practice. But as I said, the preferable setting is where we can actually solve the subroutine in closed form. And one example where we can do this and where we have shown that a closed form solution exists is for the following class of problems. So here we are on the manifold of positive definite matrices. And we have interval constraints. So interval constraints here is written with respect to the Löwner order. So as you might know, on the positive definite matrices, we have a partial order relation introduced by the Löwner order in the sense that L is smaller or equal in Löwner order than X if X minus L has only non-negative eigenvalues. So that is what this curly inequality sign here means. And that class of problems, so where our objective function is a function on the positive definite matrices, and we have such upper and lower bounds on the optimum, occurs in quite a few settings, including for barycenter problems such as the Gaussian mean problem. So here is written out the linear oracle, how it looks on that manifold. So we have inserted here the Riemannian gradient on that manifold. And then here also the inverse of the exponential map, so that, as I said, in a sense, characterizes how the geodesics look like in that space. And then we can show that that optimization problem actually has a closed form solution. I've put that here in the blue box. So it looks somewhat complicated, but it can be implemented much faster than an optimization routine. But there's some matrix inverses and some matrix multiplications, but it's one closed form solution. It doesn't require an iterative solver. So in practice, it's much faster than if we would call an iterative solver, and it's also an exact solution, so we don't have an approximation error. And if we test that in practice, that also performs competitively if we compare it with other methods. So one example of a problem that has this structure is, for instance, the barycenters on positive definite matrices, or sometimes called the Gaussian mean problem. So here we have a collection of matrices which might or might not have a weight associated with it. And then written here is the Riemannian distance. And then here our constraints, our upper and lower bound, are given by the matrix means inequality. So you know, of course, that in over the real numbers, the geometric mean is lower bounded by the harmonic mean and upper bounded by the arithmetic mean. And then if we're looking at positive definite matrices, there the barycenter corresponds to the geometric mean. And then we can also define a harmonic and an arithmetic mean of positive definite matrices. And those two can be computed in closed form. So there's a very simple equation for computing those. The geometric mean cannot be computed in closed form. So that's harder to compute, and that optimization problem corresponds exactly to this Gaussian mean problem. So we have very well-defined upper and lower bounds that are easy to compute. And then that optimization problem has exactly the form of our class of problems where we have the closed form solution. And if we plug that into an implementation of the Riemannian Frank-Wolfe method for such manifolds, we see very competitive performance here. So the Riemannian Frank-Wolfe method is shown here in blue. And then we have here, those two dotted lines are stochastic variants of the Riemannian Frank-Wolfe method that I didn't get to mention in this talk, but that we have also explored. So the idea here is that we don't compute the full gradient, but only an approximation to the gradient. So that gives an additional speed up in each iteration, and then here leads to a visible speed up of the method. And then the other methods that you see here in the plots are other Riemannian optimization methods. So those fall more into the category of projected gradient methods. And you see here that we have a significant speed up compared to those in practice. Okay.
Melanie, can you say again what the HPD manifold is? It's positive definite matrices.
Oh, sorry, symmetric positive definite matrices.
Okay.
The H is Hermitian, so for symmetric.
And then the eigenvalues can be as close to 0 as you want, but
yeah, they can't be 0, but they can be arbitrarily close. That's correct. Yeah.
Okay. Thanks.
Yeah, this is maybe also a natural point to stop for if there are any questions, since yeah, the second part of the talk is about to start. If anybody else has a question.
Can we see a few slides back explaining before the exact solution? Yeah. Before 1 second.
One further.
Before the closed form. Yes. Sorry, maybe I missed. So what is delta eta here? Delta sub eta here?
Oh, so delta characterizes the error term here.
And
so that m phi is a that's a constant that depends on the objective function. Eta is our step size. So those are this is specific to the objective function, and that's specific to the overall Frank-Wolfe optimization. And then that delta here, where's my mouse? Here, that delta characterizes the approximation error in the subroutine in the linear oracle.
Okay, thank you.
Yeah, so if this basically the message here was, if that delta is sufficiently small, right, then our overall error in iteration k is only slightly increased. So as long as that delta is not too large, basically we still converge at a sublinear iteration complexity, and our constants in that way don't become too much worse. So yeah, as long as we have a good approximation to the solution of the subroutine, then we're fine, basically. Any other questions? No. Okay, then let me continue with the second part. So in the second part of the talk, just as a reminder, we're still, of course, in the Riemannian optimization setting. So we still consider objective functions that are defined on a usually a Riemannian manifold. We again assume that those are smooth, and now we're only looking at geodesically convex functions. So I should have said, maybe I go back to this. I should have said in the first part of the talk here. So this algorithm is not restricted to the convex setting, right? We can also apply this algorithm to geodesically non-convex functions. In that case here, this X star will only be a local optimum. So in the non-convex setting, of course, there's not a unique global optimum, so we're not guaranteed to converge to the global optimum, but we can still, with a slight adjustment of the analysis, we can still show a sublinear a convergence at a sublinear rate to some local optimum. Now, in the second part of the talk, we are specifically looking at geodesically convex functions and functions with a very specific structure, namely functions that can be written as a difference of Euclidean convex functions. Right, so the components f and h are Euclidean convex. And now, of course, the difference of two convex functions is not necessarily convex. So in sort of interesting instances of this problem, we have a Euclidean non-convex objective. But this geodesic convexity condition that we saw earlier is weaker than Euclidean convexity. So there are quite a few problems that are through an appropriately chosen Riemannian metric are convex, but non-convex in the Euclidean sense. So including some of the problems that we had on the initial slide and that we will see in a few slides in the numerical examples. So basically here we are looking specifically at a class where we're sort of taking a mixed Riemannian Euclidean perspective. So difference of convex optimization has a very long history, so it's been studied for quite a while, but only from a Euclidean or a Riemannian perspective. So there's a lot of work on thinking about how we can solve those problems and taking into account that they are non-convex, so developing Euclidean algorithms for solving those problems. Those Euclidean algorithms, including the one that we will analyze here, are empirically very strong, so they are very competitive. But due to the Euclidean non-convexity, they are typically pretty hard to analyze. And then the second perspective that was taken at those problems was a purely Riemannian one. So where Riemannian algorithms were designed to solve that problem, and then also the analysis was purely through a Riemannian lens. Here we're taking a sort of mixed perspective where we are analyzing the fast Euclidean algorithm. But the tools that we're using for the analysis are geometric tools. So tools that exploit the geodesic convexity of the problem. So the algorithm that we are analyzing is not new in our work. So that's a class of algorithms that's been very popular and has been used in many different settings. It's called CCCP algorithm, so convex concave procedure. The algorithm itself is very simple and it can be derived in kind of 3 steps. So let's do that here. So we know that the component functions are Euclidean convex, right? So in particular for H, the Euclidean convexity condition, if we just rearrange terms, we get this inequality. And then this inequality we can insert into the objective function to get an upper bound on the right-hand side. So this is what I've done here. Right, and that upper bound is convex. So the idea of the convex concave procedure is to successively minimize upper bounds, convex upper bounds on the objective function. And then one can show that the sequence of values that we get from that routine does indeed asymptotically converge to the true optimum. So in a sense, so first to note, that's a purely Euclidean algorithm, right? We have used Euclidean convexity here, this right-hand side. So the actual objective function that we're optimizing in this algorithm is purely Euclidean. There's no Riemannian gradient. We don't need to implement any exponential maps, any parallel transport operators. So purely Euclidean algorithm. And then the only known convergence results for those types of algorithms were asymptotic. So basically, we were able to say that the algorithm converges, but we had no idea of saying how fast the algorithm converges. Right, that is in contrast to the algorithm that we've seen in the first part of the talk, where we could say after k iterations, we are that close to the optimum. And obviously, if we want to use algorithms in practice, we want to have some idea of how fast an algorithm converges, and ideally want to certify that, so have a theoretical guarantee, as opposed to just being able to say that the algorithm will converge at some point. And due to the non-convexity, that is very difficult to certify with just Euclidean tools. So what we were able to show is that if we exploit the geodesic convexity, so if we look at the subclass of problems where the problem might be Euclidean non-convex, but it is geodesically convex, we can use that geodesic convexity to actually certify a convergence rate. So our informally stated how our result looks like is that we assume some bounded level set assumption and impose some mild regularity conditions on the gradient of the component function h. Both of those are not very strict assumptions, so they're fulfilled for many examples where we encounter such problems in practice. Then in that case, we can prove that the CCCP algorithm converges at a sublinear rate. So again, something like on the order of 1 over k. So you see that here on the right-hand side, there are some constants that depend on the geometry of the underlying manifold on which we're working, and the Lipschitz constant of the objective function. But overall, our error decreases at a rate of 1 over k. So again, sort of similar to what we discussed in the case of the Frank-Wolfe algorithm, this is nice, right? It gives us a precise guarantee on the convergence rate of the algorithm. But to really judge how practical the algorithm is, we also have to think about how expensive it is to actually compute one of those iterations. And in that case here, that depends very much on the complexity of the so-called CCCP Oracle. So I don't think I said that, but the CCCP Oracle is exactly that subroutine. So where we are minimizing this upper bound on the objective function in iteration k. So again, we could call a numerical solver to solve that subroutine that will, lead to an approximate solution of the CCCP Oracle. So again, we would need to factor in that approximation error in our convergence analysis. But fortunately, sort of the alternative way of solving that CCCP Oracle would be if we can find a closed form solution. And it actually turns out that there are a lot of instances of problems that fall into our category of geodesically convex difference of convex problems where we have a closed form solution. And very often those can actually be already found in the literature. So for some of these problems, they're very simple fixed point iterations that have been known to be extremely competitive numerically, but there was very often no non-asymptotic guarantees, so no known convergence rates for those algorithms, even though it was numerically established that they are very fast. So our framework here really provides for these methods that the first non-asymptotic convergence guarantees. So this includes like some problems again that appear as like important subroutines in machine learning algorithms. Metric scaling, for instance, is one example. The barycenter problem that we saw earlier, Brascamp-Lieb constants, the computation of metric square roots. So many problems fall into that class of geodesically convex difference of convex functions, and for many of those we actually have a closed form solution for the CCCP Oracle. Yeah, so just to note on this other case where we don't have a closed form solution. So here there's a similar argument that we can make as we did in the Frank-Wolfe case, where we have an error term that depends on here it's called epsilon, so that characterizes an additional term that depends on on constants that are specific to the objective function or the geometry of the underlying manifold. And then the size of the term is sort of characterized by an epsilon here, and that epsilon factors into our convergence rate as a sort of constant. And again here, as long as we find a good approximation to the solution of the CCCP Oracle, then that doesn't slow our convergence down very much, and we still converge at a not much worse sublinear rate than we would have with an exact solution. So let me show some numerical examples. So the first one here is for the problem of computing the square root of positive definite matrices. If we write that as an optimization problem, this is how it looks like. This is written with respect to the so-called S divergence. And then it was known previously that that problem can be solved very fast with a simple fixed point iteration that you see here. So that was originally proposed by my co-author, Suvrit Sra. This paper only gives numerical illustration for the fast convergence. So there are no non-asymptotic rates, only asymptotic convergence guarantees. With our framework here and interpreting this as a special case of the CCCP procedure where the CCCP Oracle is solved in closed form, we can actually also explain the fast convergence that we see here in the numerics. So here you see in red the CCCP procedure, so basically just performing this fixed point iteration. And then here we compare that with a range of state-of-the-art Riemannian optimization methods. And we see here that the CCP procedure performs very competitively for different sizes of inputs. A second problem that we looked at is the problem of computing Brascamp-Lieb constants. So that's a problem that is receiving a lot of interest in the theoretical computer science community. It relates to or is a special instance of the operator scaling problem that some of you might heard of. And it has deep connections to a range of other problems. So in mathematics, there are a lot of important inequalities that can be seen as special instances of Brascamp-Lieb inequalities for specific input data and constants. So those are here the parameters that characterize the specific inequality. And then in computer science, there are also problems like maximum likelihood estimators in Gaussian models, or Taylor's M-estimator that are of a very similar form or have very deep connections to this problem. And essentially when we say computing Brascamp-Lieb constants, so what we want to do here is to compute basically the smallest constant for which this inequality is fulfilled. Okay, and then again here we're interested in some kind of epsilon accurate approximation of that constant, and we are interested in saying how many iterations do we need to compute an epsilon approximate solution. So one can show, and this map was proposed in another work by Suvrit and myself. This problem can be solved again with a simple fixed point iteration. This fixed point iteration is derived from a formulation of the problem of computing that constant in the Brascamp-Lieb inequalities that is written here. It is known, so from early work by Brascamp and Lieb, it is known that the optimum has to be positive definite. So there is we can write this as an optimization problem on the manifold of positive definite matrices. And then by analyzing this problem, we can derive this fixed point iteration. And that also fits into the framework of CCCP algorithms, again here where this map is a closed form solution to the CCCP Oracle. And then if we implement this, we have some results down here. So again, the red line corresponds to an implementation of this this fixed point iteration. And then we again here have the other lines, just our state-of-the-art Riemannian optimization methods. And we see here that the CCP procedure is very competitive. Looking at those plots, we actually see that it performs quite a bit better than the first order methods. So that's kind of a hint already that perhaps our analysis of sort of in the worst case sublinear might be a bit too conservative. So, which is in fact something that we explored in this follow-up work. So maybe just as a brief note on sort of the history of computing Brascamp-Lieb constants or what other approaches exist. So the first algorithm that was proposed for the operator scaling problem and therefore also for computing Brascamp-Lieb constants was Gruwit's algorithm. So that was proposed in 2004, and that used only Euclidean tools. So that's a purely Euclidean algorithm. And then more recently, about 15 years later, a convergence analysis for Gruwit's algorithm was proposed. So in Gruwit's original work, there was only a guarantee of asymptotic convergence. So again, no way of telling how fast the algorithm converges, what its rate might be, but that was provided in this follow-up work using actually a Riemannian perspective. So treating the positive definite matrices as a manifold, as we've done throughout this talk, and then using the geodesic convexity of this problem to derive non-asymptotic convergence guarantees for the algorithm. Now, Gruwit's algorithm also performs, is also an iterative algorithm that iterates a map that's actually not sort of conceptually not unlike the fixed point iteration that we perform here, but ours is derived from a different formulation of the problem, and motivated by this observation that the first the sublinear iteration complexity that we get from the CCCP analysis being likely conservative. If we look at the plots here, we actually analyze this problem through a different geometric lens. So the positive definite matrices could also be endowed with a different metric that actually doesn't give us a Riemannian geometry, but a Suvrit geometry on the manifold of positive definite matrices. And that gives us a different lens through which to analyze that fixed point iteration. So I don't want to go into too much details on sort of the defining the Finsler geometry, but it arises from endowing the positive definite matrices with the Thomson-Park metric, which is written here. So it's just a different metric that we put on the positive definite matrices. And then we use this to analyze this fixed point iteration. So this map that we've seen already on the previous slide. And then through this lens, the first thing that we can show is that the map, in fact, is contractive, right? So that's, of course, important for proving the convergence of a fixed point map. So this is what we show here, where dt is the Thomson metric with which we have endowed the positive definite matrices, and that just having having shown that that contractive property, that allows us to then, with a little bit of additional work, to certify asymptotic convergence of our procedure. This is subject to a suitable initialization. So basically, there's a certain set, a certain compact set around the optimum in which we have to initialize. But subject to having initialized within that set, we can show that the map contracts, and then with some additional work also show asymptotic convergence to the optimum. And then, of course, we would like to have convergence rates, so quantify the rate of contraction in order to give non-asymptotic convergence rates. And that is also possible to do in this framework. So here we have to impose some additional regularity conditions. And again, require a suitable initialization. And then in that case, we can show that the map in fact converges at a linear rate, which is what we would expect from the numerical results. And that gives us, I stated this here only informally, you can find the details in the paper, but that linear rate gives us now non-asymptotic convergence guarantees. Another word here on the suitable initialization. So I already mentioned that we need to ensure that we have initialized this map within a certain compact set that contains the optimum. We have a good characterization of that set, but we are not sure how to efficiently compute a point in that set. So that is one kind of open problem or limitation of our approach right now, that we're not sure how to. So we can basically give an initialization, we can check whether it's a good initialization, but it's difficult to compute a good initialization if we don't already have one given. So basically to compute a point within that set. But assuming that we have one, we have a fast algorithm and an algorithm whose fast convergence we can also certify. Okay, and that brings me to the end of my talk. So we've seen, we looked at a couple of different problems and different algorithms where exploiting Riemannian geometry, specifically geodesic convexity, can give us an advantage over standard nonlinear programming approaches. We first talked about algorithms in the constraint setting, so where we optimize a function defined on a Riemannian manifold subject to convex constraints. Here are some references if you want to learn more. And then in the second part of the talk, we looked at geodesically convex difference of convex functions. Here we analyzed algorithms that do not need any Riemannian tools, so that are in a sense purely Euclidean algorithms, but the Riemannian perspective allows us to certify convergence and understand why they have the good performance that we see numerically. And in the future, we hope to explore more applications of these algorithms in machine learning. Thank you.
All right, let me suggest that we all unmute ourselves and give a round of applause for Melanie. Are there questions for Melanie?
I had a question. So in some of these matrix or manifold optimization problems, you benefit greatly if you can find an exact solution for this local update step.
Yeah.
Is usually clear in advance for a problem whether there's going to be an exact solution for that local update step? Is it easy to know if there's going to be exact or not, or is it open and hard in some cases?
Yeah, that's a great question. Yeah, that's one of the kind of open directions that I think could be really valuable in this context. Understanding systematically when we have a good solution and when not. So a lot of the examples that you actually all the examples that I showed you in this talk, the numerical examples were for the manifold of positive definite matrices. So that's no coincidence. That's a manifold that we understand really well. Where there's sort of a lot of work on, different properties of those matrices, different things that we know to hold in the Euclidean setting and the Riemannian setting. So that's just a very well-studied class of problems. And this is also where we have closed form solutions, or where we have derived closed form solutions. But I don't think it's restricted to that. So there's certainly, I think if one would do sort of some more systematic analysis and try to find more closed form solutions for these subroutines, there could be a lot of value in this. They have some work that came after we proposed the Frank-Wolfe method. Some people have looked into have derived some other closed form solutions for the linear oracle. So I know there are some for orthogonal and rotation matrices for certain classes of problems that people have derived. I don't know offhand for what other problems people have looked at, but yeah, so usually if there's a class of problems where there's sort of a sufficient practical interest, then people might look at how could we approach them, can we find a closed form solution? But yeah, there's no systematic, or to my knowledge, no systematic understanding of where we have a closed form solution and where not. And for the difference of convex functions for the CCCP Oracle, here it was really that our paper did not propose a new algorithm. So the iterative map for the Brascamp-Lieb constants, that's new. But the CCCP procedures, they have been widely studied in the literature before us. And what we basically did is that we found like a common framework and a common analysis that gives a convergence analysis for those algorithms. So this table that I had here a few slides back, this is basically just interpreting fixed point iterations that have been known in the literature and been known to work really well numerically, just interpreting them in the framework that we have here as geodesically convex difference of convex functions. And there are probably many more out there. This is the one sort of that I'm aware of that we found when we did this work. But that's probably not an exhaustive list. And you know, if you look more, you probably find these structures in many other specific methods or fixed point iterations that have been proposed for specific applications that somebody has studied at some point.
Thank you.
More questions?
I'll ask one more question. So this difference of convex functions framework, how did you come up with it? Did you just sort of think of it abstractly on its own first, or was there one particular application and then you realized it was much more general and fit any other applications?
Oh, so this is a like very well studied class of problems, like in optimization, difference of convex optimization. That's like a very that's just a very important class of problems. And then our insight here was really just like bringing in this geodesic convexity angle. So basically realizing that, especially in the case of matrix manifolds, a lot of those Euclidean non-convex problems are actually geodesically convex. So that was really the realization here that there's sort of a sufficiently broad subclass of this problem class that is geodesically convex, and that we can exploit that to find non-asymptotic convergence rates. Right. So while this class of problems was well studied before, but usually if you look into the literature, it only has asymptotic convergence rates. And then you see some numerical plots and people say, oh, this is fast, it's a good method. But you know, without certifying that fast convergence and bringing in the geodesic convexity angle here, we are able to mathematically show that it has the fast rate that we see in the numerical experiments.
Thank you.
I had the same question, Henry. Yeah.
Okay.
So great. Let me go ahead and end the recording here.